Hi there, my name is Kevin. I'm going to go through a thermodynamics situation that means the transfer of energy. There are some things I want to explain in detail. I will release another video explaining them all. We're going to go through this in 5 minutes. It's for a specific situation. Okay, our specific situation is you have a cylinder-piston arrangement such that the piston can move up a track on the side of the cylinder, and it's actually going to move a distance d because a pressure P from the gas is being exerted on the bottom of it. It's moving such that at time equals 1, the volume that the gas is contained in is now larger, and that specifically means that the pressure has decreased from P to 1 atmosphere. It's at 1 atmosphere because we're at equilibrium, because the atmosphere surrounding is also at 1 atmosphere. And as I said, the piston has moved up a distance d, as you can see in this equation here, by applying a force F to it. Applying a force F is just the same as saying applying a pressure over the area of the piston. So if you rearrange the equation for pressure, force over area, you get force equals pressure times area. If you stick the force equation back in the work equation, work equals pressure times area times distance. Area times distance is the same as volume, so stick that in the work equation, work equals pressure times volume. We want to look at small increments of work because at the end we're going to add up small increments of a certain quantity, which is important to us. So now we have to look at the small increments as well. And we're going to say for each small increment of work, the volume change is much greater than the pressure change, such that the pressure change is basically equal to 0, so dP equals 0. So you have dW equals P times dV. Now, energy in our system is lost as it's expended as work is done, so at the end we have less energy in our system than the beginning, so the net energy change is negative, so dW equals negative PdV. Now that's our first equation for work. Now we're going to look for one for heat, Q. So we have to do a small description for this. As you add heat to the system, that means the parts composing the system have more energy levels available. And if you have more energy levels available, that means the parts composing the system can rearrange into a greater number of unique configurations. Greater number of unique configurations means higher disorder. In thermodynamics, higher disorder means more entropy. So that means if you add heat Q to the system, then you increase the entropy. Now how does temperature relate to entropy? Well, let's see. The fractional increase in new energy states is higher with lower temperature, since a higher temperature means more energy states. So that means if you have a lower initial temperature and you add some heat to the system, then the entropy change will be higher than if you had a higher initial temperature when you added the heat to the system. So we're also going to say when we add that heat to the system, the temperature change is so low that it's basically equal to 0. So for our case, we have, since this means Q is proportional to S, and this means T is inversely proportional to S, we can put the T in the denominator and the Q in the numerator, so we have ds equals dQ divided by T. And we're also going to have to look at the second law of thermodynamics. This is the entropy change in the universe always greater than 0, so that we have to put these small hashes over the d's, which means irreversible process, not like the work equation where it's a reversible process, but for our calculation purposes, we don't need to worry about reversible and irreversible, so ds equals dQ divided by T. And we want to rearrange the equation so that we have an equation for heat, dQ equals T times ds. Now we want to stick the heat in the work equation, both the internal energy equation, U equals Q plus W, and we want to then look at the increments for the internal energy equation, just like we did for the work and for the heat. And so then du equals T ds minus PdV. Now we want to look at another important equation that is a function of internal energy. This equation is called enthalpy, H equals U plus PV. Now expanding this equation, dH equals du plus d bracket PV. Now we substitute in for internal energy, dH equals TdS minus PdV plus PdV plus VdP, the last two coming as we extend d bracket PV. Now, as you can see here, there's two PdV, so those cancel, so dH equals TdS plus VdP. And we want to look at Gibbs Free Energy as well. That's our most important thing. It's a function of enthalpy, and so that we can expand it, dG equals dH minus d bracket TS, and substituting for enthalpy, dG equals TdS plus VdP minus TdS minus STT, the last two terms coming as we expand the dTs. And as you can see here, there's two TdS's, so those cancel, so we have dG equals VdP minus STT. Now, in our situation, we're going to say the temperature change in from time equals 0 to time equals 1 is so small that it's basically equal to 0, so then this term can cancel, which is STT, so then you're left with dG equals VdP. Now we're going to say in our system we have an ideal gas, and there's 1 mole of it, N equals the number of moles in the system, so we can substitute in for volume, V equals 1 RT divided by P. And now this volume equation we can substitute in the Gibbs Free Energy equation, so we have dG equals RT dP divided by P. Now, if you follow this arrow up here, we see now we're going to get an equation for delta G. We have to do an integral on the left-hand side and the right-hand side. We do it on the left-hand side, then we simply will get delta G, but if we do on the right hand side, we have to consider the pressure change. It goes from P1 to P2. As we said before, P1 is equal to P, which is greater than 1 atm, P2 is equal to 1 atm. So if we substitute in here, we have on the right hand side RT, we take the integral sign, and we have from P to 1 dP divided by P. Now, in our case, we have to flip that over because we always integrate from smaller to larger, so we have to do a negative sign, and then we can flip the integral 1p, and then we have dp divided by p, so then we have on the left-hand side again, delta g from before, equals negative RT ln p. P goes from p to 1, sorry, it goes from 1 to p, so then we have delta G equals negative RT ln p minus ln 1, but ln 1 of anything equals to 0, so we have delta G equals negative RT ln p. That's our first equation. That's for the specific situation of gas expanding and its pressure decreasing from time equals 0 to time equals 1, and from there we're going to do a more general form of this Gibbs free energy equation next video.